Welcome to this second recorded video for the Part B lecture notebook in the fourth module. In this video, we will be discussing Monte Carlo integration, and you can click here for a link to the Wikipedia article on Monte Carlo integration, and it also has an illustration that is useful for another part of this lecture notebook. The basic idea of Monte Carlo integration is to estimate the integral. I'm going to just no, that was too large. I'll shrink that. There we go. Is to estimate the integral of a function f of x over a set A using the average of a random sample of function values. The pertinent question is, how do we generate a random sample of function values in order to do this? Well, we generate a random sample of the x values in the set A, and then we evaluate the function f at these random inputs. Then we simply compute the sample average of A. Are there any sticky points to this? Well, a few simple examples will illustrate just about all you possibly need to know for the purposes of our notebook. Suppose the function f of x is equal to 5 on 0 to 1, so it's much like the velocity we were studying before, that when it is constant. From our previous example involving velocity and conceptualizing the integral of a real valued function with a univariate input as the signed area between the curve and the horizontal axis, we know that the integral should be 5. So this is what our MC estimate, our Monte Carlo estimate, should be approximating. Well, in fact, any random sample of x values between 0 and 1 will always produce corresponding function values of 5 because the function is constant on this interval. So what would the sample average be of these randomly sampled function values? Well, 5, of course. In this case, the MC estimate is exact. That's fantastic. Well, what about if f of x was 5 on the interval 0 to 2? So all we have done is change the set from 0, 1, the interval 0, 1, to the set 0, 2. We know the exact answer should now be the integral of 5 over the interval 0, 2 should be given by 5 times 2 minus 0, 10. 5 times 2 is 10. However, by the same exact reasoning, any random sample of f of x values will produce a sample average of 5, not 10. What if f of x was equal to 5 on the interval 0 to 0.5? Well, the exact answer again is 2.5, yet any sample average of f of x values will produce 5, not 2.5. So what is going on? Well, we need to weight the sample average by the size of the set A. In summary, if x sub I is denoting a set from I equals 1 to n, of points in A is a uniform random sample from the set A, and we let mu of A, mu for measure, denote the measure, meaning the size of A for an interval would be the length, then an MC estimate of the integral is given by this. The length of the measure of A, in this case the length of an interval, times the sample average. A sample average is just obtained by adding up, if you're not familiar with this notation, this is a summation, sigma for summation, and you're summing up from I equals 1 to n, all of your function values, and then you divide by n. You multiply by 1 over n. This computes the sample average, and then you multiply by the measure of the set. So if you notice, this would fix all of these things above, because even though the function value sample average would always be 5, the measure of A, the length of the interval, is 2, and it would correct it to 10 here and correct it to 2.5 in this case. So here's a suggested activity. Add a useful docstring to this function, compute the 1D Monte Carlo approximation to a function to describe the role of the various parameters, and add some doc tests. I'll explain kind of what's going on. So for this function, compute 1D MC approx, you give it a function f, a, b, and n. This looks much like what we've seen before, except there's no rules. It's the Monte Carlo approximation. There's no rectangle rules. So I want to approximate the function over a univariate function over an interval from a to b. N is going to become the number of uniform random points I pick from a low value of A to a high value of B. Like I said, this is something we've seen before. This module on computational applications is using all these various things that we've seen in previous lectures. The measure of the size of A, the set A, the integral, the set we're taking the integral over, is just the length of the interval from A to B, which is B minus A. So that's giving us mu of A, which I denote by the variable mu sub A, and it's just equal to B minus A. I use the mean function in NumPy to compute the mean, the average value of the function values on these random points. That's that average. That's going to be computing this right here, that summation times 1 over n. That's going to be given by this mean function. That's all you have to do there. And then I just have to multiply that average function value by mu of A. And then I want to return the average function value as well as the MC estimate. I want to return both as a tuple. So let me run this. And now let's do some numerical experiments and analysis. Below, what we show is how to use this function defined above and understand its variability due to random sampling. Because every time you run it, even if n is fixed, you generate a different set of uniform random numbers. We want to analyze the rate of convergence, and we want to create interactive visualizations that help us tell a story. So we'll go to the same function we've seen before, and now these all look the same, but they're going to be different. Look what I'm doing. I'm creating an integral approximation for this function f from a equals 2 to b equals 4, and n is going to be 100. And I am returning the second component. Remember, Python indexing starts at 0 because I want the Monte Carlo estimate of the integral. And then I run exactly the same line of code and I print the output. And then I run exactly the same line of code and I print the output. Now look at the 3 outputs I print. They are all different. Now one of these is actually, it turned out, to be close to the answer we know, which is negative 1.72. But 2 of them are quite a bit off. And if I run the code cell again, well, they're all quite different. And it will keep being different every time. What we see is the issue involving random sampling of points in that interval a to b to generate an approximation of the average value of the function. As you can see by rerunning that code multiple times, there can be quite a bit of variability. Below, we compute 1,000, actually I had 10,000 here, but I'll make that 1,000 approximations, and we visualize the results with a histogram. So the number of trials, the number of times I'll compute a Monte Carlo approximation will be given by 1,000. I am going to store 1,000 of these approximations in a NumPy array that I initialize to zeros. And then for each I, from basically 0 to 1,000, that's what this will do, I calculate an integral approximation using the same line of code so that I can observe the variability with 100 points. And now what I do is I plot a histogram of these integral approximations, and I produce a vertical line that shows what really the exact, we're using the quad function to produce an exact value of the integral, and so that will be in black. And so there you go. You see that the Monte Carlo approximation produces what we call an unbiased estimator of the integral, meaning its average value, which aligns with the true value. It's some variability here because of finite sampling. I've only produced 1,000 approximations, but that's basically what you're expecting to see from Monte Carlo. You get a distribution of answers. So the histogram is centered around the exact value, which is good, but the variance is quite large, which is bad. If you're trying to approximate a value that's negative 1.72 and you're getting values that are near negative 5, you're not always producing good approximations. Now, to look at what the actual mean was of this integral approximation and to compare it to the quadrature rule, look, the mean approximation is actually quite good. So this is basically all the approximations and then take the mean. So while any single Monte Carlo estimate may be bad, its expected value is quite good. It is an unbiased estimator, as I was just mentioning, but the variance is just clearly far too large with 100 samples. So how do you reduce the variance? Increase the number of points. So again, I'm going to do 1,000 trials, so this runs quickly. I am going to do our log space of n's, so this is going to be using 100, 1,000, and 10,000 points for the number of random points. And then look what I do. For I in the range of 3, for j in the range of number of trials, I will then create an integral approximation I stored in this 2-dimensional array of size 3 by number of trials. I compute these various 1D approximations with these n's. You should really comment every single line of code here and explain the shape and what's going on. That is a very good thing for you to do. So I'm going to run that. It will take just a second. If I make this 10,000, it could take a few more seconds, but with 1,000, it's not too bad. Now I'm going to plot 3 histograms on top of each other, all on the same axes. And there's going to be for these different integral approximations computed with different numbers of samples. Let's go ahead and plot that here. So in blue, we're seeing the histogram of approximations to the integral when we use 100 random samples. And you see how wide the histogram is. And then when we use 1,000 samples, we get a much narrower histogram. And when we use 10,000 samples, we get an even narrower histogram that's more concentrated around the mean value. What we see is that increasing the number of random samples reduces the variance in the MC estimates, the Monte Carlo estimates. In other words, each individual Monte Carlo estimate is more likely to be closer to its mean value for a larger n compared to a smaller n. Since the mean values are all the same, remember the MC estimates are unbiased, this means that a larger n value is more likely to produce accurate estimates of the integral. It is more common to use the standard deviation to quantify variability in estimates around the mean value than the variance because it is in the same units as the mean value. The standard deviation is simply the square root of the variance. It can be computed using a built-in function within NumPy as I show below. And that's what you want to analyze with the rate of convergence because the expected value of our Monte Carlo approximations are good. You want to look at how quickly you're reducing the variance around those estimates, the mean of that Monte Carlo estimate. So I have a log-log plot and I plot the n's and then I plot the standard deviation of my approximations and notice that axis equals 1 because of the shape here where each row has a fixed size of the number of points used and then I'm just repeating it a number of trials, the 1,000 times. So I want to compute the standard deviation across the rows, across the columns, not down the rows. And so now when I plot this, we see a curve that's very much like what we saw before with the rectangle rules. We see a simple line that seems to suggest that we reduce by about 1 order of magnitude the standard deviation with 2 order of increased number of rectangles. In fact, we use our polyfit to create an estimate of the rate of convergence, where again we return the slope of this line of best fit, and we print it and we see it's about negative 0.5. So we had to increase 2 orders of magnitude. This is actually wrong to say number of rectangles here. This is number of random samples. So that'll be fixed when you get it. Number of random samples. We have to use 100 times more random samples to decrease the error by 1/10. All right, that's what this means because we have to go 2 orders of magnitude in this direction to decrease by 1 order of magnitude in this direction. That's what a negative 0.5 is. So this above value is approximately negative 0.5, which is actually the theoretical rate of convergence guaranteed by the central limit theorem. And I just point out, you really should, if you have not taken some probability theory and statistics classes. You don't need these things for what I'm giving. You can just use the code I'm giving and interpret it as I'm telling you. But it's very useful for just a more deep appreciation and understanding for what I'm saying. At any rate, I've already explained this in terms of order of magnitude, but you can read it again. So the question is this worse than the left, right, or midpoint rules for the deterministic models? Yes, it is. Except there is a huge caveat here. The geometric methods for approximating integrals only work in extremely low dimensions. Geometric or other deterministic quadrature or cubature methods, as they're known, for approximating integrals suffer from what is known as the curse of dimensionality. You should look this up. What is the curse of dimensionality? We will not dwell on this here other than to say that as the dimension goes way up, the quality of the deterministic estimates goes way down unless an exponentially increasing number of points are used to estimate the integral. However, the rate of convergence for the MC estimate is independent of dimension. However, this doesn't quite tell the whole story. It is a big reason why random or pseudo-random approaches to estimating integrals are actually preferred in high dimensions. But we won't dwell on this here. So now we create a visualization. We're going to plot the MC estimate in 1D of a function. And what I'm going to do is use my function to compute the 1D approximation, and everything else is just for plotting. Let's look at what the plotting produces. So here I do my interaction with a widget, and I run interact with n equals 100. So I do this because as you change, you might want to rerun it with the same fixed value of n. So now I run interact, and now what I'm showing in purple, what I'm plotting, so in gray is the exact area under the curve, or it's the area under the curve visualized. And what I'm showing in purple is the rectangle defined by the average value of the function. So our average value of the function in this case is giving us something that's about 5.39. If I run it again, it gives me about 5.18. If I run it again, it gives me about 3.56. If I run it again, it gives me about 3.7. And this is keeping n fixed. But what happens if I made n 79,450? I just ran it there. Now what do I get? 3.88. Run it again. 3.89. 3.97. 3.88. So notice the variance, how much these numbers are differing from one run to the next, is much reduced by having a much larger n than a smaller n. Like at n10, look at the values. 2.93, 6.95. That's a lot of variance. It's moving around from one interaction to the other. So you can play around with this, and you can see how I generated the different patches there by looking at this. So this is my average rectangle. So then I have an activity involving Monte Carlo integration. Again, feel free to create many new code and markdown cells as you work through it. So you should complete the wrapper function that I showed. So I started one, and I say you need to complete this part here and this part. And I have the instructions that in the code cell below where you want to complete this, we now assume n is a list of integers. Like before, in the previous activity with the rectangle rules, n was a list of the number of rectangles. Now n is a list containing the different numbers of random points used to approximate the integral. The wrapper function also has an additional parameter, numTrials, which is an int type that specifies the number of times, i.e. the number of trials, to repeat the approximations for each value in the list of n values. The default numTrials is set to 10. So I've defaulted it to 10. So there's some additional instructions here, but I think you can finish reading. And you notice this is basically the same level of complexity of the wrapper function that I asked you to complete in the activity involving the rectangle rules. So if you're looking at all these videos first, you might want to do actually this activity. You might find this activity to be easier because I did give this structure here as opposed to in the first activity. And then I want you to do things that are very similar to the first activity, but I spell out the differences as they matter here. And then we get to what happens if the set A is complicated. So I'm going to make another shorter video for this part of the lecture notebook, and that will be the last one for the integration notebook part B lecture notebook of the 4th module for this class. Thanks for listening, and I'll talk to you in the next video.